now. And now you can start. Okay, good morning. We continue our discussion. In the last lecture, we have seen about the pipelined architecture design. Advantage of the pipelined architecture or parallel pipelined architecture, right? So how do we improve the throughput of the circuit? By just inserting the intermediate registers. That means we needed to divide our entire application into small modules, or your big Boolean equation into small modules, so that we can able to improve the throughput. That means we are reducing the latency. So our clock speed will be increased to the reduced latency speed. So that will obviously increase our computation speed or throughput. In the laboratory afternoon session, we are going to see these things in design also. We'll take one equation, then we will divide that equation. So how the stages are getting updated for different rising edges subsequently, right? That we will see in the afternoon. So to understand that concept with one example, we have started one fast array multiplier. Fast array multiplier, FAM. In the fast array multiplier, we are going to multiply n number of bits by n number of bits just by some addition. Right? Even we no need to go for the AND gate operation also in FAM, and we are going to make one lookup table. With the help of that lookup table, you can just complete the multiplication by some additions, right? That is why it is called fast array multiplier. There will be a table, therefore it is called array, right? So after some Boolean expression and discussions, we came to know that finally the product P can be represented by this way: A7 128 into X plus A6 64 into X, where X is an integer now. X is an integer. That means our intention was multiplying A by X. We replaced the A by its equivalent binary representation. Correct? No summation k equal to 0 to n minus 1, a k 2 power k. That is nothing but a model of the binary number, right? Mathematical representation of the binary number. So k will vary from 0 to the LSB to the MSB, right? Then we substituted that representation in that equation. Then finally we got this one. So still our X is in the integer form. X is in the integer form now. Because this is not an issue in FPGA design, because we can deal the computation either in binary or in integer or signed number, unsigned number, floating point number, fixed point number, include and also the complex number, right? So this is the equation we got now. Now my intention is I am going to formulate one lookup table, right? Lookup table is nothing but I am taking the X here. This is the X value, and this is the 2X value, right? And this is the 4X value. This is the 8X value. This is 16X value. This is 32X and 64X and then 128X. 128X now, right? So table will be something like this. So as we progress in our lab session, you will understand how to create the array or the table. String array, numeric array, complex array, integer array, floating point number array, whatever it is. Our FPGA is more sophisticated and a lot of degree of freedom is there for our design. Right. So X is, suppose I am taking X is 0, 1, 2, 3, 4, 5 and so on. In this case, the X will go up to 255. Why 255? Because we are taking 8-bit now, 8-bit multiplier now. The table is for 8-bit by 8-bit multiplier. 8-bit by 8-bit multiplier. 8-bit by 8-bit multiplier. That is why the X value is restricted to 255. If you take 9 bits, then accordingly it will be, value will be 12 bits or 14 bits or 128 bits, your X will go now. Your X will go now, right? So X can go to any value because you can multiply 128 bits by 128 bits in the FPGA now, which is not possible by any other platform. 128 bit by 128 bit multiplication is possible in the FPGA. Even in the ULSI board, they are telling 228 bits by 228 bit is possible now. So when you multiply 128 bit by 128 bit, your result will be 2 into 128 bit maximum result, correct? No? So that much a long register, that much a long computation, multiplication is possible in the FPGA. So we no need worry about the array declaration or using the array design in the FPGA. So here it is restricted to 255 because right now we are interested only for the 8-bit multiplication, right? Now you take 0, 2x, the x is 0 means 2x also 0, 4x also 0, 8x also 0, 16x is 0, 32x is 0, 64x is 0, and 128 bit also, 128x also 0. When you take 1, then your 2x is 2, 4x is 4, 8x is 8, here 16, here 32, here 64, and here 128. Here 128, right? Then when you take 2, if x equal to 2, your x equal to 2, then what will happen? This will be 4, correct? No? This will be 8, this will be 16, this will be 32, this will be 64, and then this will be 128, this will be 256. 256. You understood, no? So like that you fill up for 3, 4 and 5. 3, 4, 5 you fill up karo. 6, 12, 24, 48, 96, 192, 384. For 4, 8, 16, 32, 64, 128, 256, and 512. For 5, 10, 20, 40, 80, 160, 320, and 640, and so on. And so on here. And finally for 255, 510, 1020, 2040, 4080, 8160, 16,320, 32,640. Which is not at all possible in the basic embedded system or basic controllers. Can you multiply 32,640 by any number? Not at all possible. But here it is possible. Here it is possible now, right? So we made the lookup table. Remove your TB and show me your face, all of you. Shashank. Right. So look here. Look here. So this table is be formulated now. This table is a standard table because we are interested right now for 8-bit by 8-bit multiplication. So we made this table as per this equation now. X is taken from 0 to 128, I mean 255, and then we multiplied by 2, 4, 8, 16, 32, 64, 128, because this is as per this equation now, right? Now, this LUT is available. This lookup table is available in the array or in the memory now, right? So the idea is, suppose I want to multiply P, one example, I want to multiply P is equal to 3 into, right, 3 into, or I will take something like this. Maybe I'm taking here 8 into 3, 8 into 3. I want to multiply 8 by 3 now, 8 by 3. That is my intention now. This is the X. This is the x now, right? This is the x now. And you convert this integer into STD logic. That means integer into binary number. Integer into binary number in 8-bit. So what is this 8 now in 8-bit? 0, 0, 0, 0, right? And 1, 0, 0, 0. And 1, 1, 0, 0, 0 is the binary equivalent of 8. Binary equivalent of 8 now. Correct, no? So that means int x is here. Int x is here now. So look this value now as per this equation int x. This is multiplication. This is the p now. So the first number, that is the 8. This may be something a into x now. P equal to, from our general form, p is equal to a into x now. So a is converted into binary and x is taken as integer only. That is the way how we proceeded to this equation, right? We got this equation by keeping x as an integer and a in the binary form. A in the binary form now. Now look here. So this position is nothing but 2 power 0th position. This position is nothing but 2 power 7th position. Correct? No, 7th position. And x into this value is 0. X into this value also 0. X into this value also 0. So all the value will be 0 except this value now. So since the x is here 3, since x is equal to 3 now, since x is equal to 3, I should go to this place. I should go to this place in the array. Because this is the x value now. This is the x value now, right? No, this is the x value now. So in my array, in the algorithm, if x value equal to 3, then I will reach this value. This x value equal to 3 now. So now I am going to concentrate on this row now. I am going to concentrate on this row now. In this row, the first bit is 0. Correct? No? Therefore, this value is 0. Second bit is 0. Therefore, this is also 0. So this is also 0. This is also is 0. You understand now? All of you getting me? So this portion is a 0. This has no magnitude because x into 0, 0. X into 2 power 1 also 0. Right. X into 2 power 3 also 0. But x into 2 power 4. This is there now. 2 power 0, 2 power 1, 2 power 2, 2 power 3 is there now. So this value only will have the value. Then this portion also is 0, this portion also is 0, this portion also is 0, this portion also is 0. So something I'm writing like that. Here, this portion is nothing but this portion, no, 0 into 3 plus 0 into 3 plus 0 into 3 plus 0 into 3 plus 1 into 3 plus 0 into 3 plus 0 into 3 plus 0 into 3, right? But this position is equal to, this LSB position is equal to this value actually. Correct? This position, this magnitude, 3 into this magnitude, the whole value is equal to 384. And this whole value is equal to 192. And this whole value is equal to 96. But 96 should be taken into the summation if the binary is 1. If the binary is 1. If the binary is 0, then that particular element will automatically becomes 0. Will automatically becomes 0 now. You understood, no? Because here 0 means there is no any value to that magnitude, that position now. Right? So automatically x into that 2 power 7 will become 0. Right? X into 2 power 7 in the sense this value will become 0. 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 Only this value we got to add now. So in our summation, if you write here, only 24 will be there. Only 24 will be there. Remaining all the elements in that particular row will be 0 because the binary magnitude is 0 now. Because it is the binary magnitude is 0 now. Already we have seen here, right? In this representation, this is the 2 power 0, 2 power 1, 2 power 2, 2 power 3. But if 0 is there, then the 2 power 2 has no value. It has no value. Since here 0 is there, then 2 power 0 has no value now, right? That the position value is 0. That the position value is 0 in the sense, in this row, this position becomes 0 now. Right? This position becomes 0 because the A7 is 0. If A7 is 0, then 128x automatically becomes 0. Right. So these are all nothing but our A, capital A, nothing but in this case A7 to A0. A7 to A0 now. So if you look this equation, when A7 is 0, you no need to add this value. Understand? When A5 is a 0, you no need to add this value because A5 is 0, therefore 32x it automatically becomes a 0 now. Right? Then this value becomes 0, this value becomes 0, this value becomes 0. So wherever 1 is there, we need to add only that value now. That means the addition, multiplication of 8-bit by 8-bit is done here just by adding some numbers. Just by adding some numbers now. Right? I'm taking one more example. Example, P is equal to, I want to multiply 5 divided by 255. Tell me the answer. 5 divided by 255. You no need to go for AND operation. Understand now, and then right shift operation. Because if you want to multiply here, this bit will be 8-bit again. Because you need to multiply 8 bits now. So you represent this number also in 8 bits. Then your algorithm becomes highly complicated. That means you need to pass them in the AND gate. Then you have to take the first one. Then you multiply them, put it in the array. Then another one you lay low. Right. Then you left shift it. From there you organize your results. Again one more AND lay low. You got the idea now. But in fast array multiplication, we no need to go for anything, such operations. Directly you need to pick up some elements from the LUT. Because all the values are distributed here. It is something like that. All the values are there. Based on your value, you take this one, add karo. You got the idea? You take this one, add karo if you need it. Otherwise, don't take all those things now. So that is why it is called a fast array multiplication. You tell me the value for this one now. 255 ke liye. I am writing in 8-bit 0, 0, 0, 0.
2610.
2610.
Yes, sir.
P equal to 2610. That means I will write it now first. 0101 into 255. Right. That means what are the elements we need to add? This is LSB now. This is LSB. Therefore, 255 will be there. 255 plus 0, 1, 0, 2, 0. Is it correct?
Yes, sir. 1275, sir.
Yes, sir.
1275.
Correct. Check karo mistake. P equal to what? 5 into 25. What is the result you got, all of you?
1275.
1275.
I will give you one more example before going to the. Any doubt on this design now?
Sir,
Ah,
sir, will it be beneficial to take the smaller number as a A?
No. I don't have value here. No, that is why I am taking. You can take any value. You can take any value within 8 bits.
If you are multiplying two numbers, then it would be more beneficial for us to take the smaller one as A, right?
That correct. That is good always. But that A and B is not in your control, no. Suppose if A is 254, B is X is 255.
Okay.
You will get the advantage of only 1 bit, no. But that is there. You are correct.
Okay, sir.
You are correct. Any more doubt on this one now? So here addition is happening. In a fraction of second, your multiplication will be over. But just you need to pick up 2 elements or 3 elements based on the binary value. You add them together. Addition ke liye we are going to introduce the pipeline architecture. Correct. So that there is also high speed addition. So that is why this structure, this algorithm is called the fast array multiplier. You no need to worry about this LUT because a lot of resources are available in the FPGA. You can build there because now we can create a 255 order FIR filter. 255 order FIR filter means you need 255 coefficients. All the coefficients are at the single precision floating point number. Totally 64 bits are there, or 32 bits are there in single precision. Double precision 64 bits are there. 128-bit floating point resolution also is there. Right. So we no need to worry about the array creation or LUT creation. So LUT we can be created. You can pick up the value and you can add them now. Right. One more example I will give you. You add and tell me the result. P equaled 254 into 255. 254 into 255. Tell me the result. Tell me first the array values. Then you tell me the final result. All of you practice. एक बिट मिस्टेक होता है ना पूरा रिजल्ट गलत होता है आपका बाइनरी में वो मुश्किल है थोड़ा so what is the first value from the array just it is here taking the lot this value this value this value this value this value this value नहीं चाहिए ये चाहिए खत्म बोलो
32640 plus 255.
oh, slow what is the first one
640 plus 255 plus 510.
one second 32640 plus
255
255
plus 5110
plus 510 plus
1020
1020 plus
2040
2040 plus
4080
4080
plus
that's all
82.
plus
Yes, sir.
8160 also
And 128
total product you are telling final product P equal to
64570.
64570 that's all right so in 8 bit mein right in the same way you can calculate for 9 bits 32 bits 64 bits so no problem there so just here the multiplication of 8 bit is done just by picking the appropriate elements from the table or lookup table and then adding them together will give us the multiplication right so this is called fast array multiplier the array term came because of this array now table right in our FPGA we are going to deal in array only something like that x11 xij right xij we got running a loop there that loop will pick up the value now if this value is 0 take this value if this value is 0 take this one otherwise leave them right so ignore that value so such a way we are going to design in the FPGA for this multiplier now right so if
Sir?
no doubt
So in this case, we added all the values except 255.
except
255.
255 is added no they told me 255 254 ke liye you have to leave only one bit no last bit you should leave
The last bit is 255.
Yes, sir. Sir,
then how did it then how you people told me 255 you people told me then
So that looks incorrect.
that is wrong correct
64770.
So 255
We got
should
to
not
add
be
it.
included in
yes
that,
yes
right?
yes
Or-
yes so because this value becomes 0 no 254 ke liye LSB becomes 0 so other than this value we got to add every values so 3264 1632 16320 plus 8160 4080 plus 2040 plus 1020 plus 510 will give you the result is it correct result is correct
66970
Result is
answer.
correct, sir. Result I considered 510 only. I didn't consider 255. So
so result is correct 64570
Yes, sir.
fine okay so now we came to know that a lookup table creation and then selecting the appropriate elements in the table based on the binary value of A will solve the multiplication of 8 bits. Now, how do you implement this one with the pipeline architecture in the FPGA now? So I am drawing the structure something like this. You take this structure. summation means adder. Addition. Here my P equal to A into capital X, capital A into capital X. So I am writing here this is nothing but A naught X, A1 2X, A2 4X, A3 8X, A4 16X, A5 32X, A6 64X, A7 120X, A7 120X, A7 120X. Then this will go there. This will come here. This result will come here. Finally, P will come out. Finally, P will come out. Let we understand this operation first. From our previous example, we came to know that, listen, this table consists of all the possible values, right? Because the value of A and the value of X is not in our hand. The value of A and the value of X is not in our hand. Therefore, the value should have all the value should have all the possible values here, right? So all the possible values are in this table now. From this equation, if A7 is 0, then this value will not be added, or this value will be taken as a 0. This value will be taken as 0. If A5 is there, then this value will be taken as 0. A5 is 0. If A4 is 1, then this value will be taken as 0 now, right? Now, any mistake in this result, one message is coming there, you multiply by calculator.
Sir, 64770, sir.
No, when you multiply 254 into 255, कितना आ रहा है calculator में?
64770.
64770.
64770.
When you add all those things, also 64770 is coming, or what?
Yes, sir.
Then how you are getting different values then? One is telling 64570, one is telling 64 again 570. So check karo. Huh? Okay, fine. So the idea is now, so what we are taking now, this value is here now, this value, right? This A naught X, A1 2X, A2 4X, A3 8X, A4 16X, 32X, 64X, 120X is there now, right? Look here in this adder, if A naught is 1, then this value will be taken. A naught is 1, bit is 1, means that value will be taken. If A1 is 1, this X value we know, right? If X value is 5, we should go to the 5th row now. We should go to the 5th row. If X is 12, we should go to the 12th row. In the 12th row, this is the first element, the second element, the fourth element, third element, fourth element, fifth element now, right? So by looking the X value, you will select the suitable row. By looking the A value, binary form, in binary form, we will come to know whether this value has to be added or not, this value has to be added or not, or this value has to be added, or that should be taken as 0. Automatically, if your X is 64, we are going to 64th row. In that row, if A6 is 1, this value will be added. If A7 is 1, these two value corresponding to that, these two place, these two cell corresponding value. You understand the idea, no? The value that we are going to take from the table. So that value and this value will be sent to this order. These two value will be sent to this order. So this order is a generic order, common order. If the A naught is 1, this value will be taken. If A naught is 0, this value will not be taken. So these two will be added here. These two will be added here. these 2 bits will be added, these 2 integer number will be added here, then that result will go here, this result will go here, in between the carry will be propagated inside, right? So that much delay we need to wait here now, that much delay we need to wait here. But this stage, no need to wait for this carry to come here, because that stage that will be taken care in this summer now, right? So this will be taken care. First stage summation, second stage summation, third stage summation, then finally output will come out now. That means here the entire 8-bit multiplication, I mean addition corresponding to the 8-bit multiplication is divided into 3 stages here. So this adder takes care of only these 2 per number, this takes care of only these 2 number, this care of these 2 number, like that. Then final result will come out now, right? So this stage, when these values are available, because these values are available at an instant of time now, so all the adders are working. You got the idea, no? All these 4 adders are working. Then the result will be forwarded into this adder now. Result will be forwarded into this adder now, right? Then this adder is also working. Then that will be passed into this adder now. You got the idea, no? Since all are the combinational circuits, we have to introduce the pipelining stage here. So I am introducing the pipeline here. Here one pipeline stage. Here another pipeline stage. Here one more pipeline stage. Right. And then output pipeline stage is already there. Output pipeline stage is already there now. Now look here, clock is given. The clock is applied into this summation also. Right. This is the clock now. Now look here, this is the stage 1, this is the stage 2, this is the stage 3, this is the output. This is the product output stage now, this is the input. This is the output stage now. Now what happened? You apply the clock now, you apply the clock here, then whatever the value is here will go inside. Then this adder will start working now. Then the result will be stored here. Right. Apply the another clock now. Apply the another clock now. Then this result will come here. Then this stage will accept the new input here. Understand? Then when this stage is working for the maybe T0 input, this stage will work for T1 input. Apply the another clock now. This stage will work for T0. This stage will work for T1. This stage will work for T2. Apply another clock. Result will come out for T0 input. And this stage will work for T1. This stage will work for T2. This stage will work for T3. And go on and so on. So this computation will keep moving. Right now. So in the previous case, suppose when I do not insert the pipelining stages here, then after applying the one input, I have to wait till getting the final output. Because before the time I cannot feed any new input here. Right? So the latency is slightly higher in the previous case. So when I slice the entire operation into chota stages, then obviously my latency came down. Therefore, my throughput will go up. So you can introduce the pipelining stage within the adder also. Within the adder circuit also, we can introduce the pipelining stages. We will see in the subsequent lectures. You got the idea now? So this is the way how the fast array multiplier is working now. Nowadays, the IP core is available for fast array multiplier. A soft IP core, hard IP cores are available. Just we need to incorporate them to get our multiplication done within few nanosecond or within few fraction of second. You understand now how this fast array any doubt you can ask me in the fast array multiplication. Good. If no doubt, we move forward. The combinational circuit is over. Combinational part is over. We need to realize all those things in our laboratory, right? Then we are moving into sequential circuit now. But I already told you, sequential circuit is nothing but some combination of combinational circuits only now. There is no any special element called sequential circuits. Again, the flip-flop latch also made up of with some gates only, basic gates only, but there is a timing control. Because of the interconnection of the flip-flops or latches, it is possible to maintain the circuits at one stable state. right? And then to change that state, we needed to feed the clock, right? So that is the idea. That is why it is called a sequential state, because all the operations will be in sudden sequence, predetermined sequence, right? S0 to S1, S1 to S2, S2 to S3, then maybe S0, again S5, S6. Based on sudden conditions, the circuit flow will move, right? Flow will move from one state into the another state is in the well-defined sequence or order. That is why it is called sequential circuits. And in the sequential circuits, there is an additional input called clock or trigger or enable, disable, latch, whatever it is. Fine. Before proceeding into sequential design, right, asynchronous sequential circuit or synchronous sequential circuits, we needed to discuss about an important section, that is a digital clock manager, DCM. Digital clock manager. I'm telling you, in your life, if you become the design engineer, FPGA design engineer, at least you should pronounce this word once in a day. In the factory, when you start doing your design, no, at least you should say DCM once in a day, because DCM is the heart, DCM is the liver. Correct? No, for any design, DCM is called digital clock manager. Digital clock manager. Digital clock manager, right? The digital clock manager, no, this is the heart to all the design, because this fellow only will manage the time control of every unit in your design, every module in your design, every section in your design. He is like a boss, right? All remaining, all the subsections or modules, units, no, they are like the slaves. They are the slaves means this fellow knows when that fellow should be triggered, what is the speed to that fellow, when that fellow speed should be increased, when this section should be given input, when this section output should be passed into the subsequent section. Everything is in the kind of this DCM only now, right? So for example, I can make you to understand the significance of the DCM. Suppose I am taking one application. This is the FPGA, right? This is the FPGA. Suppose I have connected here one sensor. This may be some temperature sensor, right? I will draw a rough diagram, right? Practically it will not be so, just to give you the idea, right? Then I have here one 7-segment display. 3 7-segment display is there. Right. 7-segment. This is the 7-segment display. 7-segment display. And also I have one antenna here. Zigbee antenna. Zigbee antenna now. Right. So this is my design. So my intention here is, my application is, I needed to measure the temperature. Suppose here maybe something. This is the flame. Assume, don't assume it is a tree, it is flame. You take it is flame. So I have the sensor here now. This is the sensor. The sensor will measure the temperature now. Will measure the temperature. And it will inform to the FPGA, right? Right? It will inform to the FPGA means lot of other signal processing is there, but that we will discuss in the subsequent module. Right? So assume now sensor is giving the information to the FPGA now. The FPGA should display the temperature value here in the 7-segment display. At the same time that it has to transmit it to the remote receiver unit. Remote receiver unit. Some unit is here, right? So it has to be transmitted to this unit. This unit is the observatory point. Assume now, right? Now 2 things are there. One is the transmission should be at a high speed. At a high speed. You understand, no? Transmission should be at a high speed. For example, I am telling you 10 kilobits per second. The transmission speed should be 10 kilobits per second. But whereas the 7-segment display should be in the low speed. Should be in the low speed. Why it should be in the low speed? Otherwise you cannot read. Suppose if I display the number 0, 1, 2, 3, 4 in the 7-segment display at the rate of 1 megahertz, can you read anything? you will see that all the segments are glowing. All the segments are on, correct? No? But FPGA is capable of driving the unit at any speed. 400 megahertz, 800 megahertz, FPGA is capable. But our eyes are incapable to sense them. You understand now? Suppose you see my finger. Now you tell me how many times I moved my finger. How many times I moved now? 2 times, right? Now you tell me how many times I moved now? 4 times. Now can you tell me?
No, sir.
Because our eyes are incapable to sense such a speed. Correct? No? So in the supplication, if you display the 7 segment number at the rate of 1 kilohertz or 10 kilohertz speed, nothing will be seen. Our eyes will see that all the LEDs are glowing, all the segments are on. One thing. Second thing, suppose I got one stepper motor here. I got one stepper motor here, 4 coil stepper motor. I want to rotate this stepper motor shaft. Can I feed the control signal at the speed of kilobits per second? Stepper motor will not rotate. Only one sound will come. You understand, no? So there are limitations. So this fellow should be operated at that speed. This should be operated at this speed. DC motor के लिए दूसरा speed है, stepper motor के लिए दूसरा speed है, piezoelectric actuator के लिए दूसरा speed है, 7 segment display, RS-232, Zigbee. You understand now? Then RF module, LCD, multi-segment display, GLCD. So there are different modules has to be operated at a different speed now. Understand? But your FPGA will be powered by 100 megahertz onboard clock. 100 megahertz onboard clock. So this is the blood to the FPGA now. So this 100 megahertz onboard crystal clock is there now. This fellow only will feed the clock into FPGA. FPGA is going to work with respect to that clock only now. With respect to that clock only. You understand now? So that is the triggering clock. That is the blood to the FPGA now. If you stop that clock, nothing will happen inside because everything will work based on the clock speed only. Right? But because since the 100 megahertz is the blood into the FPGA, but all the modules within the FPGA cannot be operated at that speed now. In some modules should be 1 hertz, some modules should be 10 kilohertz, some modules should be 1 megahertz, some modules should be 200 megahertz also, some modules should be 400 megahertz also. You understand now? Therefore, the DCM is the block which is available in the FPGA, which has the capability to reduce the master clock rate or increase the master clock rate. So here the master clock is normally represented by M clock is equal to M clock means this is not the function. This is not the keyword. My Guruji told me use M clock for master clock for your understanding. So I am also telling you. So master clock means M underscore clock. M underscore clock is the onboard clock. That is typically 100 megahertz. Typically 100 megahertz now. Correct? No? So you can increase this one to 400 megahertz or you can decrease this one to 1 hertz. Even less than 1 hertz also. Less than 1 hertz also is possible by using DCM. Digital Clock Manager now. So digital clock manager is the very essential unit in our design because you are feeding the onboard clock into digital clock manager. That fellow will generate 0.1 hertz, 1 hertz, 10 hertz, 400 megahertz, right? So increasing the frequency from 100 megahertz into 400 megahertz is called interpolation, upsampling, right? Interpolation means increasing the sampling, increasing the clock speed now. So that what we called interpolation or increasing the clock speed, where we needed to do the multiplication operation, int operation. For increasing the clock, you need to multiply the onboard clock by certain factor, maybe 2, maybe 4, maybe 5, maybe 6. You understand, no? But in the reduction of the clock, I want to reduce the clock. In that case, you needed to go for division. Then 100 megahertz divided by 2, 100 megahertz divided by 4, 100 megahertz divided by 8 now, right? So the division operation in the DCM will give us reduced clock. Multiplication operation in the DCM will give us increased clock. Will give us increased clock now. So the DCM is a very essential unit which need to be familiar to all of us to complete our real-time designs. So this is the DCM. DCM. I'm giving here M underscore clock, right? M underscore clock. Then from here, I will get to so many clocks. You can get n number of clocks from this DCM now, right? So this may be 1 hertz, this may be 10 hertz, this is 100 megahertz, 100 megahertz onboard clock. This may be 10 kilohertz, this may be 1 megahertz, this may be 150 megahertz, this may be 400 megahertz, this may be 0.001 hertz. You understand now? And this may be 100 hertz. The idea is 100 hertz will go to certain module in our design, right? And then 0.001 hertz will go to some other module now. So there will be so many modules here. You got the idea, no? So many modules. I mean, this DCM, here will be so many modules in the design. So this will go here, this will go here, this will go here, this will go there. So this is our complete FPGA design. The idea is your master clock should be applied into the DCM, and then you have to make the DCM to generate the record clock. Then all your other computation modules or the sub design units will be operated with respect to that generated clocks, that appropriate clock, right? So as we progress, you people will be familiar in choosing the clock. Suppose LCD के लिए क्या कितना clock rate चाहिए, 7 segment के लिए what is the clock rate, correct? No, GLCD के लिए what is the clock rate. So all those things are available in the product data sheet or in the user manual now. So you need to generate that clock rate to operate them now. You got the idea? So digital clock manager is the very much essential unit which will give us the record clock to handle different modules or different units in the FPGA design at a different speed. At a different speed in the sense at a different data rate or at a different frequency, because obviously they should be operated at that speed only, you considering their nature of job or nature of the operation or maximum speed of the operation now. You got the idea? Did you understand the DCM now? So DCM.
Sir,
Yes.
the types of clocks DCM generate, it is fixed or it is variable according to the peripherals?
According to the peripherals, you should generate it. It is variable. It is completely user control. You can design any clock. That is, nothing is defined there, but the procedure is defined. Based on that procedure, you can generate any clock you want. Number of clock also is user defined, and the speed at every clock also user defined. For example, you can generate 50 clocks, you can generate 100 clocks, you can generate 10 clocks. There is no any limitation for that, provided if you have the resources in the FPGA. For example, Vertex 6 board has a lot of resources than the Speton 3 board. Speton 3 may only 2 DCMs are there, but Vertex 6 board may 8 DCMs are there. So resource is important. Based on the available resources, you can use them. But no more any limitations or constraints based on the design point of view. Nothing is there. Any more questions in DCM? Okay, we will continue now. How do we design the DCM? DCM बोल रहे, but ऐसा हम करेंगे. वो question है ना अभी आपका सारे साथ. So now I'm taking one example. In this model, we are going to discuss about the reduced clock. Second model, we are going to discuss about the increased clock, right? Now, assume my clock rate is, M clock is 4 megahertz. 4 megahertz, right? My onboard, you listen this one, this is very, very important, right? Because your life starts from these things only now. From all our future designs, everything based on DCM only now, right? If DCM nahi hai, aap nahi hai. Understand? Clock is 4 megahertz now. My intention is, this is the FPGA. I am going to create one DCM. My onboard clock rate is 4 megahertz. I want generate 1 hertz here. I want generate 1 hertz now, right? How do I generate now? That is a question. How do I generate now? To understand this logic, the clock divider logic, we should understand one thing now. That is, what is a 4 megahertz first of all? 4 megahertz in the sense, suppose this is 0, this is 1 second. What is the frequency first of all? Anyone can tell me what is frequency?
Number of cycles per second.
What?
Number of cycles per second.
Number of cycles per second is correct. Correct. Number of cycles per second is correct now. Right. Good. That means in this case, no. Number of pulse, we call this number of pulse, right? In sinusoidal signal number, we call this number of cycle. Here we call this number of pulse, right? That means 1, 2, 3. That means 1. First clock is applied, rising edge. 2, second clock is applied. Third clock is applied, right? And so on. And this is the last clock. This is the last clock. What is this clock number? When the 4 megahertz is the speed, 4, 1, 2, 3, 4, 5, 6 hertz. Hertz, right? That means hertz is nothing but pulse per second. Pulse per second. Right now, number of pulse per second, 1 divided by t. The idea is here, within a second, how many pulses we are applying here? 40 lakhs. 40 lakhs pulses, correct na? So within a second, this crystal applies 40 lakhs pulses, right? Did you have seen any time this crystal clock, any time crystal source? It is a very chota fellow. It is like this only. That's all. Very, very small in size, crystal oscillator, right? But that oscillator is capable of generating 40 lakhs pulses within a second without any issue in the rising edge, falling edge, logic 1, logic trigger. I mean logic 0. Kitna clever aadmi hai. Understood? No? 40 lakhs pulse is coming out within a second without any changes in its shape. No jitter. No jitter means the one is moving like this. Aisa nahi hai. Very perfect one. One, this much. They like this, like this, like this. So it is keep pumping the clock into the FPGA now. So 40 lakhs clock is going into the FPGA now. It is a very small chota admi, but it has the capability to generate 40 lakhs pulses within a second. Then it goes into this FPGA. Right? You come to this FPGA, how clever this fellow is. This fellow is capable of capturing them without missing any pulse. You understand, no? Kitna clever these two devices are then. Suppose, for example, I am taking Magna, right? I am asking Magna to, I am giving you idli, you eat that idli, right? So I am 1 second, one idli I am throwing her. You understand? Throwing towards her mouth. 1 idli, 1 second. She can catch, she can eat also. 10 idlis per second, 100 idlis per second, 1000 idlis per second. You assume now, can she able to face that speed first of all? But either aisa nahi hai, this chota fellow is pumping 40 lakhs clock into FPGA. This FPGA is also reading it at the same speed without missing anything. You understand now? So this fellow is capable of reading it. Not only 4 megahertz, 10 gigahertz also this fellow can read at that nowadays, right? Because direct to RF digitization is there now. So RF SOCs are there. RF boards are available in ultra large scale integration now. So if 40 lakhs, then if it is 40 megahertz, 400 lakhs pulses, correct? No? Then 400 megahertz, then 400 lakhs pulses into going into this FPGA. This person is capable of generating it. This person is capable of receiving it. This fellow is not only receiving, but also he is capable of performing all the computation at that speed. You understand now? So the computation also happened that speed now. So your output will come out. Right. Now the question is how to handle all such a high speed pulses. To speed now, 1 Hz clock. Acha. Okay, we stop now. Then we will continue. Maybe next class. Huh?